6.2, real applications of normal distributions. This section presents methods for working with non-standard normal distributions. So last time we did standard, this time we're doing non-standard. And basically what that means is the mean does not have to be 0 and the standard deviation does not have to be 1. It could be anything. Last time when we did standard, it had to be a mean of 0. It had to be a standard deviation of 1. Now it can be anything. What's going to end up happening is we're going to have to convert our non-standard into a standard. So we'll end up doing the same thing as what we did in 6.1, but we have to get there first. And so we've got a conversion formula. We're looking for this z-score, and they're going to give us an x number and a mean number, that's mu, and sigma is your standard deviation. They're going to give you some of those numbers. You got to find a z-score so we can do exactly what we did last time. The formula allows us to standardize any normal distribution. When I say standardize, I'm just trying to get the mean equal to 0 and the standard deviation equal to 1 out of whatever we started with. So when you look at these two pictures, basically the one on the left is non-standard, and the only difference really is you've got some kind of mean, and you're going to have some x score, where in the standard normal distribution your mean is 0 and you're talking about a z-score. So you standardize it to get to the z-score, and you want to do that so you can look at that table. So we talked about this z-table with all these numbers. You have to get to the z-scores in order to use this table. Number 1, what proportion of men are taller than the 72-inch height requirement for shower heads? Heights of men are normally distributed with a mean of 68.6 inches and a standard deviation of 2.8 inches. Find the percentage of men who are taller than a 72-inch shower head. Okay. So first thing I would do maybe is just kind of write down what they give us. And they're giving us a mean of 68.6 and a standard deviation of 2.8. So we start with that. This is how it's different than the last lesson. Last lesson, it was always a mean of 0 and a standard deviation of 1. Now it could be anything, and including weird stuff. All right. So this number over here, 72, this is our x number. And x is just whatever specific number we're looking at the time. For our problem, whatever it is, we're looking at 72 and how it compares to the mean, I guess. So if you look at your normal curve, normal curve is bell-shaped. And last time when we did standard normal distributions, that was the mean and it was 0, but the mean doesn't have to be 0. In this case, the mean is 68.6. And so if you think about this specific problem is talking about 72 inches, and we want to know something about the people that are taller than 72 inches. So we're looking at this. What percentage of that curve is on the right side of that number 72? All right. So we've got a couple of different ways of doing this. One way is to standardize the curve. Change it from this into something more standard. All right. So how you do that is you need to get a z-score. And we've got a formula for that. Z equals x minus the mean over the standard deviation. In this case, that's 72 minus your mean was 68.6, and our standard deviation was 2.8. So we want to calculate that. 1.21. We get 1.21, and that's our z-score. That's our z number. We did that calculation. We got z equals 1.21. And so essentially what we've done is we've taken this curve and we've standardized the mean to 0, and the z-score is 1.21. Maybe it's a little bit easier to understand. We're 1.21 standard deviations away from the mean, okay? So what we would do now, if we didn't have a calculator, if we don't have a calculator, we can look at the chart for this z number, 1.21. So we find 1.21, a z-score of 1.21 in this chart. And so think about how this works. Here's 1.201. That means 1.21 corresponds to this number right there, 0.8869. That's the area under the curve, but you got to know how this chart works. This chart is only giving you the area under the curve to the left of that number. So we just found 0.886, what was it? 9. The area to the left is 0.8869, and that's exactly what we don't want, right? That's saying 88% of men are shorter than 72 inches. We want taller. How are we going to find taller? Let's just subtract 1 minus 0.8869 is 0.1131. It says what percentage? Find the percentage, so I'm just going to call it 11.31%. Think about if that makes sense. About 11% of men are taller than 6 feet tall. Okay, I'll buy that. I'll buy that. That's the answer. All right. Now, think about this if we had a calculator, because we actually should be able to use our normal CDF function in this calculator. So second vars and go down to normal CDF. C stands for cumulative. So the way we would have done it yesterday is we would have gone from lower bound was 1.21 and the upper bound was basically positive infinity. But we don't even really have to standardize it if you think about it. This function will work for our numbers. So our lower number was 72, and our upper number we need to go to basically infinity. We need to go all the way over to the right. So that's why I just type in a bunch of 9s. Type in a bunch of 9s to make us go way over to the right and fill in the right side of that graph. The mean was 68.6, and the standard deviation was 2.8. Hopefully this works. Yeah, okay, 0.1123, okay, 0.1123. Now, notice that's a little bit different than our answer we got was 0.1131. But if you think about it, didn't we round off our numbers earlier? When I got that 1.21 number, I had rounded off. So technically, this number in the calculator right now is better than the number that I wrote down on my page, because the number that I wrote down on the page and the number I used in the chart, all that stuff was rounded off slightly. Either way, you're right around 11%. Okay. So make sure you know how to use the table. Make sure you know how to use your technology. Example 2, Air Force height requirement. The U.S. Air Force requires that pilots have heights between 64 inches and 77 inches. Heights of women are normally distributed with a mean of 63.7 inches and a standard deviation of 2.9 inches. What percentage of women meet the height requirement? All right, so I think it makes a lot of sense to draw a picture. So we're going to have a normal distribution, so normal curve. And the mean is 63.7. And we want to know something about between 64 and 77. So what we are interested in is between here is 64 and here is 77. We are interested in the area under the curve in that region right there, or the percentage that's under the curve right there. All right. So what percentage of women are in that little band between 64 and 77? So it's kind of tricky here because if you've got a calculator, this is a pretty easy question. You just type it in. If you didn't have a calculator, you're going to need to use the Z table. In order to use the Z table, you need Z numbers, and that's where that formula comes in. So what we would do is we would find this Z score, we would say X minus the mean, 63.7, over the standard deviation was 2.9. Okay, 64 minus 63.7 all over 2.9 gives me about 0.10. Okay. And then we do the same thing for the 77 right here. We go 77 minus 63.7 over the standard deviation, 2.9. So 77 minus 63.7 divided by 2.9 is 4.59. Like that. Now I've got some Z-scores. I've standardized this. I've got some Z-scores. And the reason that's useful is because I can look at the table now. All right. I look at the table and basically, well, wait a minute. I can't look at the table because 4.59 is not going to be in the table. The highest, if you look at the numbers in the table, it goes up to 3.49 basically. That's as high as it goes. So I can't even really use the table there. But maybe I didn't need to in the first place. All right. Think about our calculator. We can do it one of two ways. If we use the Z-scores, let's do what we did yesterday. Normal CDF, and you've got your lower number is 0.10, and your higher number is 4.59. Those are your two Z-scores. And when I standardized it, I had a mean of 0 and a standard deviation of 1. Okay. So let's type that in. Second vars, normal CDF, and it was a 0.1 and a 4.59. 0 was my mean, standard deviation of 1. I get 0.4602. 0.4602. Okay, but think about it. That calculator doesn't make you standardize. The only thing that makes you standardize is the Z-table. If you were using the Z-table, you have to find those Z-scores. But if you're using the calculator, you don't really need to. You could instead do normal CDF, and then just do your X numbers. Your lower X number was 64, and your higher one was 77, and your mean was 63.7, and your standard deviation was 2.9. We should be able to just type that in. Second vars, normal CDF. Oh my gosh, I can't get it. Stop. And the lower was 64, upper was 77, mean was 63.7, and the standard deviation was 2.9. Paste it in, home screen, 0.4588. Notice it's not the same. 0.4588. It's not the same, but that should make sense though, because when I used the 0.10 and the 4.59, I rounded off. My numbers aren't quite right. I had to round off the first time through. This time I didn't round anything off. This answer is actually better. Okay, this answer is actually better, 0.4588. But let's answer the question. What percentage of women meet the height requirement? Let's just say 46%. It's about 46%. So then this slide says finding values from known areas or probabilities. We're just going backwards. If you're using the chart, you just use the chart backwards, okay? If you're using a calculator, it's a little bit easier. If you're using a calculator, you're going to have a new function, inverse normal, okay? So you input the area, the mean, the standard deviation, and then you select left or right or whatever. So you're going to have 4 arguments in there, 4 things to plug in. But if you're using a calculator, you can use the inverse normal function. Otherwise, if you're using the table, that's fine. You're going to use the table. But one thing that's weird is you're going to have to convert. You're going to have to use that conversion formula again. So it's the same formula as before, but it's actually maybe more useful to use this version. All I did was isolate x. If you take that formula and isolate x, you've got this. That's going to be useful for us because we're trying to find the x. We're going backwards. Number 4, refer to the sketch. It's always going to be useful for you to think about that bell curve and where we're looking at and what we're finding the area of. So the next one is actually example 3 here, designing an aircraft cockpit. When designing equipment, a common criterion is to use a design that fits 95% of the population. Approximately 46% of women satisfy height requirements for the U.S. Air Force. What would be the maximum acceptable height of a woman if the requirements were changed to allow the shortest 95% of women to be pilots? That is, find the 95th percentile of heights of women. Assume that heights of women are normally distributed with a mean of 63.7 and a standard deviation of 2.9. So I noticed some people kind of struggling with 95th percentile and what that means, but go back and look at your picture again. When we're talking about a normal distribution, 95th percentile is talking about the bottom 95%. So what this problem gives us is the bottom 95%, and we want to know what this number is right there. Okay, whether it's a z-score or an x number or whatever, we want to know what that number is. All right, I guess specifically in this problem, we don't want a z-score, we want an x number. Okay, so it says we've got a mean of 63.7, standard deviation of 2.9. Okay, so a couple of different things that you can do. If you did not have a calculator, you would want to use your chart, use your table, okay? And you use your table backwards. When they give you the area, like this 0.95, you use your table backwards. So in your table, what you'd have to do is find 0.95. And so 0.95 is like right in between these two. Right in between those two would be 0.95. So it's 1.6, and then in between these two, we'll call 0.45. I could call that 1.645. 1.645. That's your z-score. So if I standardize it, I would have a mean of 0 and a z-score of 1.645. That just means 1.645 standard deviations away from the mean. So what do? Well, we need to find an x number. That's going to be easy because I got everything I need. All right, I can just use the conversion formula. That's the conversion formula from before. But remember, it might be useful if you isolate the x. So maybe it would be more useful to use this version of it. X equals mu plus z sigma. And I know that formula seems hard to understand, but it kind of makes sense if you think about it, okay? We want to start at the mean, 63.7, and we want to add 1.645 standard deviations. We're going 1.645 standard deviations away from that mean, so we're going to add 2.9 1.645 times. All right, I think it makes a lot of sense if you think about it that way. So we punch that up, 63.7 plus 1.645 times 2.9, and we're going to get 68.4705. So our answer, we want to find what would be the maximum acceptable height. We're looking for this x number right here, right? It's 68.5. 68.5 inches. Now, that seems like a lot of work, and maybe it is. But if you've got a calculator, it can be a lot easier than that. Okay, I know I'm going to use the inverse normal function, and I know that because they gave me the area. I'm going backwards this time. I'm not finding the area under the curve. I was given the area under the curve. So how this function works is you're going to enter that area. Okay. And then if you go 0 and 1, you're going to get the z-score. So second vars inverse normal, okay, 0.95, 0, 1. Our tail is left. That's talking about where we color in. We're coloring in the left. And that gave me my z-score of 0.1645, okay? That was my z-score of 1.645. But I wonder if we have to even find that z-score. Can't we just find the x-score? Let's see if we can do this without having to standardize it. Second vars inverse normal. Okay, the area was 0.95. The mean without standardizing it was 63.7. The standard deviation they gave me was 2.9. Left. There it is, 68.5. Okay. So it's kind of cool that you don't really need to standardize it if you've got a calculator. It'll do the heavy lifting for you. You still have to know what you're talking about because sometimes it's the left side and sometimes it's the right side and sometimes it's in between. All right. When do I need to standardize it? Well, I need to standardize it to use the table. Okay. So if you just use this red equation, you're not there yet. You'd still have to do the conversion. It's going to be much more efficient if you just do inverse normal 0.95 comma 63.7 comma 2.9 left. I believe if I'm not mistaken, some of you with older calculators, you won't enter that left in there. You won't have that option, okay? But that's going to give you your 68.5 directly. That's the most efficient way. Should there also be a minimum height requirement? Well, this isn't really a math question, more of a common sense question. Yeah, so they can reach all the stuff. Okay, so that might be an answer. Yes, so they can reach all controls.